Welcome. So in this tutorial, we're going to look at second order linear differential equations with a right-hand side that's not zero, and so those are non-homogeneous. So the general technique we need to apply here is to find the homogeneous solution, which is to impose a zero on the right-hand side, solve that, and then add to that a solution we obtain from a guess, called the particular solution. So the general solution is the sum of the homogeneous solution and the particular solution. So I think I'll probably attempt to go through the first 13 questions here on the left. So let's get started. All right, question 1. We have y double dash minus 5, y dash plus 6y equals 2x minus 7. Okay, and so first let's find the homogeneous solution. So step 1 is to solve y double dash minus 5, y dash plus 6y equals 0. So we impose a 0 on the right hand side. And so that's called our homogeneous solution when we find this. Okay, so we write the characteristic equation. So the characteristic equation is lambda squared minus 5 lambda plus 6 equals 0. So what I've done there is I've just looked at the coefficients 1, minus 5, and 6, put them there, there, and there, and next to those is lambda to the power of the number of times we differentiated that y. Okay, so twice, once, and no times. And there we have the characteristic equation. Okay, we can factorize this one because 6 is 2 times 3 and the sum is 5. So lambda minus 2 times lambda minus 3 equals 0. And we get lambda 1 is 2 and lambda 2 is 3. All right, so this gives us the homogeneous solution y as a function of x, but I'll put a subscript h for homogeneous, is equal to a e to the lambda 1 times x, so 2x, and then plus b e to the 3x. I'm taking the lambda 1 and the lambda 2 and putting them in the exponents. All right, so here's our homogeneous solution. Now for the particular solution, so to find a particular solution, what we need to do now is make a guess, but it's an educated guess based on what the right-hand side looks like. So we guess, because this is a polynomial, we're going to guess a polynomial here. yp equals, I want to choose lowercase a, x plus lowercase b, all right, not to be confused with this a and this b. Okay, and so I put ax plus b here because it looks like this, all right? So if this is a polynomial on the right-hand side, then I need to guess a polynomial for my particular solution, but I choose one to have the same degree as this, so degree 1, degree 1. And I need to find a and b, and so the way I do that is by differentiating enough times to sub it into this equation and match coefficients. Okay, so differentiating, we have yp dash is a, and then again yp double dash is 0. Okay, so substituting this into our differential equation, so substituting into the ordinary differential equation, y double dash minus 5y dash plus 6y, except let's put subscripts p on these. This is equal to 0 minus 5 in brackets yp dash, which is a here, and then plus 6 times yp, so ax plus b. All right, and this is expected to be equal to 2x minus 1. Sorry, minus 7. Okay, and so we want to expand now the left-hand side and compare that to the right-hand side. So let's do that, expanding. We get 6ax plus 6b minus 5a equals 2x minus 7. And so now we can match coefficients. 6a must be equal to 2. 6b minus 5a must be equal to minus 7. So we get 6a equals 2, and we get 6b minus 5a equals minus 7. Now this is a simultaneous linear system that we need to solve here. But it's easy to solve because the first equation here, we can just divide that throughout by 6, and this gives a equal to 1/3. 2 over 6 is 1/3. Now if we sub that 1/3 back into the second equation, we get 6b is equal to 5/3 minus 7. So then b equals 5/3 minus 7 all over 6. Okay, and so simplifying this, placing this minus 7 over 3, we have 5 minus 21 all over 3. Then multiplying top and bottom by 3 gives us 5 minus 21 over 3 times 6 is 18. So 5 minus 21 is minus 16. 6 times 3 is 18. Now we can reduce this fraction and say that this fraction is equal to minus 8/9, canceling a common 2. So b equals minus 8 over 9. Okay, so now that we have this, we can express our particular solution because it's ax plus b, lowercase a and lowercase b. So we get yp equals 1/3 x minus 8 over 9. And we can even tidy this up by factoring out a 1/9 out of this. So this is 1/9 of 3x minus 8. Okay, now the general solution y as a function of x is equal to yh for homogeneous solution plus our particular solution yp. And so in this case we have a e to the 2x plus b e to the 3x, and then plus 1/9 of 3x minus 8. And here is our general solution. Okay, let's move on to the next question. Question number 2. So we have the same left-hand side, but a different right-hand side. (132x squared minus 388 x plus 1077). Okay, so we already know what our homogeneous solution is based on the previous one. So we have y homogeneous is equal to a e to the 2x plus b e to the 3x. And now we need to make a guess for y particular. So this is polynomial here on the right hand side, and now what we need to guess is a polynomial of the same degree. So yp equals ax squared plus bx plus c. And now we need to differentiate this so that we can sub this into the left hand side. So yp dash here is 2ax plus b, and yp double dash is just 2a. Okay, now substitute into the differential equation, and we have 2a minus 5 brackets times yp, which is 2ax plus b, and then plus 6 times yp, ax squared plus bx plus c. Okay, now this is equal to the right hand side, 132 x squared minus 388 x plus 1077. Now what we need to do is expand the left hand side and match coefficients. So expanding, what we get then is 6a x squared plus 6bx, but over here we have a minus 10ax. So let's collect like terms here while we're at it. So plus 6b for this times this. Leave the x on the outside. Here we have a minus 10a, and that's times x. All right, next we have plus 2a. Then we have minus 5b for the product of minus 5 and b. And then we have plus 6c. And this is equal to 132 x squared minus 388x plus 1077. Okay, now you can see that this is going to give us a simultaneous system of 3 linear equations in lowercase a, lowercase b, and lowercase c. So we get 6a equals 132. Then we get 6b minus 10a is equal to minus 388. And then we get 2a minus 5b plus 6c is equal to 1077. Okay, now we need to solve this system. Now 132, that's clearly even. It is, let's see, 66 times 2 is 120 plus 12. I think that's 132. But you know what? I'm just going to get out Mathematica here. And we're going to calculate. Okay, so 132 over 6. What does this reduce as? 22. So clearly we have A equals 22. Okay, so what does that give us for B? So B is equal to, taking this minus 10a over to the right hand side, we have 22 times 10 is 220. So 220 minus 388 is minus 168. Now if we divide this by 6, we have minus 28 for B. All right, now given that we have A and B, we can find C quite easily. So C will be 1077 minus 2 times A plus 5 times B, and then that's all divided by 6. Okay, so it looks like we get 893 over 6 for C, if I've done that calculation correctly. I think so. All right, but let me know if I'm wrong. All right, so putting this back together, we have now our particular solution. So yp equals 22x squared minus 28x plus 893 over 6. All right, and so now we can add to that the homogeneous solution and express our general solution to the differential equation. So y of x is equal to y homogeneous plus y particular, which is a e to the 2x plus b e to the 3x plus 22x squared minus 28x plus 893 over 6. All right, let's move on now to question 3. So in question 3, we have the same left-hand side, but on the right-hand side, we have an exponential function. Okay, so what we need to guess now is that the particular solution is an exponential function. We know that since we have the same left-hand side, we have the same homogeneous solution that we found previously. So y homogeneous is equal to a e to the 2x plus b e to the 3x, and we guess that yp is equal to lowercase a e to the power of 5x. Right, so something of the same form, but we don't know the lowercase a here. Okay, so let's differentiate this. So yp dash is 5a e to the 5x, and yp double dash is equal to 5 times 5, or 25a e to the 5x. Okay, so taking these three, substituting those into the left-hand side, we have y double dash minus 5y dash plus 6y equals 25a e to the 5x minus 5 times 5a e to the 5x plus 6a e to the 5x, and this is equal to 13e to the 5x. Okay, let's expand and simplify the left-hand side. So 25a minus 25a is 0 times e to the 5x. So we just get 6a e to the 5x is equal to 13e to the 5x. And so then 6a is equal to 13, and we must have a is equal to 13 over 6. So therefore we've got yp is 13 over 6 e to the 5x. And this gives us our general solution. Y as a function of x is equal to y homogeneous plus y particular, which is a e to the 2x plus b e to the 3x plus 13 over 6 e to the 5x. All right, let's move on now to question 4. So in question 4, we've got a first order differential equation on, or at least order 1 on the left hand side, right? So we have y dash minus y equals e to the x. And so in this one, we're going to use the same methods we've used previously to do this. And then in question 5, we're going to solve the same differential equation using methods for exact equations. So we're going to do this one in 2 ways here. All right, so first, let's find a homogeneous solution. Then let's find a particular solution and take a sum of those, because those will be hopefully independent or linearly independent solutions. And so a sum of linearly independent solutions gives us our general solution to this differential equation. Okay, so let's begin. So begin by solving y dash minus y equals 0. Okay, and so this one is clearly separable. So let's note that it's a separable differential equation, and so we can take that y over to the right hand side, then divide by y, and we get the integral of 1 on y with respect to y is equal to the integral of 1 dx. Okay, and so we have the natural log. So I'll write ln for your sake, natural log, but I would normally write log to mean log to base e. So we have x plus c. Okay, and so then solving this for y, it gives us y homogeneous is equal to e to the power of x plus c, which we can write as a e to the x, because we break this up as e to the c times e to the x, and e to the c is another constant which we call a. Okay, so here we have our homogeneous solution. So now let's find a particular solution. So next we guess yp is equal to, now the reason why I'm going to guess a, lowercase a, x e to the x is because up here we happen to have the same form as what we got in the homogeneous solution. So when that happens, you have to make a slight variation of this guess, because you're hoping to find a linearly independent solution independent to this one that you got in the homogeneous solution. Okay, and so that's why we guess this in this case. So now we differentiate twice. So yp dash, oh no, sorry, just once, because we only have one single derivative there. Okay, so yp dash is, now we need to use the product rule for this. So when we use the product rule, we pull one of these out. So ax times the derivative of e to the x, which is e to the x here. But then we swap this around, and so we have e to the x times the derivative of ax with respect to x, and so we get a e to the x. Okay, so we've used the product rule here, so let's say by product rule. Alright, so fantastic. Now we take the two of these and sub those into our differential equation. So yp dash minus yp is equal to ax e to the x plus a e to the x minus ax e to the x. Okay, great. And so we can see that these two here vanish. We just get a e to the x, and that's good because we can match that to what we expect to get here, e to the x. And so we see we must have lowercase a equal to 1. Okay, and that gives us our particular solution. So yp equals 1 x e to the x, or just x e to the x. And so our general solution is y as a function of x is equal to y homogeneous plus y particular, which is a e to the x plus x e to the x. Okay, fantastic. Let's do the same thing again using methods for exact equations. And so if you want to review that, go look at my previous tutorial number 4 on this topic, where we solve some exact equations. Okay, so let's do this again. And I'll set this aside so I can pull it up and show you that hopefully we get the same thing. Well, I just need to put this out of the way under my coffee cup, maybe. Okay. Good. Now, let's see. We've got question 5 to do, which is to solve the same differential equation again using methods for exact equations. So remember, we want to rearrange this so that we have a function of x and y plus another function of x and y times dy on dx equals 0. Okay, and so let's take this y over to the right hand side. So we have y plus e to the x is equal to dy on dx. But let's take that dy on dx over as well. So we have minus dy on dx. And so that's equal to 0. Let's put this as minus 1 here. And so we'll say plus minus 1 times dy on dx. And let's put a bracket around this. So I'm thinking of this as my function p, and this is my function q. However, we can see that this equation here is not exact. And the reason why it's not exact is if I differentiate this first function here on the left partially with respect to y, I will get, and so let's just do this, differentiating partially with respect to y, we get just a single 1. But if we differentiate with respect to x, the minus 1, well, we have 0, which is not equal to 1. All right, so this differential equation is not exact. However, we can multiply through. So multiply by a function of x and y. Let's call this an integrating factor, so that the result is exact. Okay, and so then we have y plus e to the x times uppercase I minus I dy on dx equals 0. Okay, and so what we do here, since we're insisting this is exact, so we let p, a function of x and y, be equal to y plus e to the x times I, and we let q, a function of x and y, be equal to minus I. All right, and so now, since we're assuming this is exact, let's differentiate p with respect to y. So differentiating p subscript y for the partial derivative of p with respect to y is equal to, now we need to use the product rule on this. So what we have then is y plus e to the x I subscript y, and then plus the other way around. And so I have I times the partial derivative of y plus e to the x with respect to y, and so we just get 1 for that. And so we have I times 1, and so we'll leave that as I. Now, this is meant to be equal to q subscript x, given that we have assumed that this is exact now. And so this is equal to minus I subscript x. And so now let's put this all together, right? Because this equals this, so we get I subscript x plus y plus e to the x times I subscript y plus I equals 0. Okay, fantastic. Now, we want to choose the more complicated one of these partial derivatives to be equal to 0, and that would be I subscript y because it comes next to this. So, guess that I subscript y is equal to 0. Okay, we only need to find one I that makes this thing exact. And so then that would be di on dx equals minus I. So what I've done, since this is 0, it zeros all of this, and then I take this over to the right hand side and express this in this way because I can see that this is separable. Okay, and so let's integrate both sides and find our integrating factor I. So integrating we have the integral 1 over I di is the integral of minus 1 dx. Alright, and so the natural log of I is equal to minus x. And so now we find our integrating factor. I don't want the plus c, incidentally, because, or even the plus g of y, because I only want one integrating factor that makes this thing exact. Okay, so I don't need this as general as possible. So I, as a function of x and y, is equal to e to the minus x. Okay, and notice, incidentally, if we differentiate this partially with respect to y, we do have 0. So this works out. Okay, so now what we have found is that e to the minus x is our I. So we come back to this and expand this out here. So we have y e to the minus x. Now e to the x times e to the minus x is 1. So plus 1. And then minus e to the minus x dy on dx equals 0. This is exact now. Okay, and so now what we want to do is find our function f. So we find f of x and y such that p, which is y e to the minus x plus 1, is equal to f subscript x, and q, which is equal to minus e to the minus x, is equal to f subscript y. So let's label these equation 1 and equation 2. So we want to solve this for lowercase f because f xy equals c will be our general solution. Okay, and so let's solve these for lowercase f at this point. All right, so integrating the first equation, we have f is equal to the integral of y e to the minus x plus 1 with respect to x. Now this is a partial integral, even though I write an ordinary d, right? Because that was a partial differential equation there, or a partial derivative there on the right-hand side. Okay, so integrating this partially with respect to x, so I can bring the y out here. So in other words, we can express this like this, and then plus the integral of 1 dx. This integral is easy. It's just minus e to the minus x. So we have minus y e to the minus x for this, and then we have plus x over here. And then since this is a partial integral, we need a function of the other letter, so g of y. All right, so we have f looks like this, but we need more information on what g is, and so we need to differentiate this partially with respect to y in order to compare with equation 2. So differentiating with respect to y, we have f subscript y is equal to, now this we can allow to move through the differential operator because this is not a y, this is the other letter x. So this can come through, and so we just differentiate y, which we get 1. So we have minus e to the minus x. Okay, this derivative gives us 0 because that's not a y. So we treat it as a constant, and then we have plus g dash of y. And now we compare this to what we have in equation 2. So equals minus e to the minus x. Okay, and you can clearly see that these two terms vanish in this equation. So we get g dash of y is 0, so g of y is just a constant. Integrating this, we get a constant. Okay, well that's pretty easy here. So that tells us then that f of x and y is x minus y e to the minus x, and then plus a constant. Alright, now this is equal to another constant, say b, in our general solution, and so if we take this over, we get yet another constant, and so our general solution looks like x minus y e to the minus x is equal to b minus c, which let's just call that d. All right, now how does this compare to what we got earlier? Now earlier we got our general solution as a e to the x plus x e to the x. Okay, now to see that this is actually the same, let's multiply throughout by e to the x. Okay, and so when we do that, we have x e to the x minus y equals d e to the x. Okay, now let's take the y over, take the d to the x over here, and then swap sides, and we get y equals x e to the x minus d e to the x. And now to compare this, we just let a be equal to minus d, and so we have y of x equals x e to the x plus a e to the x, which is what we got earlier, right? And I'll even show you the page we made earlier. Here it is, question 4. This is what we got. So arguably this is a fair bit easier, right? Okay, let's move on now to question 6. So question 6 asks us to find the general solution y double dash minus 2y dash plus y is equal to x squared minus 1. All right, so our characteristic equation, so in other words, we're going to solve the homogeneous solution first, solve for that. So we've got lambda squared minus 2 lambda plus 1 equals 0. All right, now this one has a 0 discriminant. B squared minus 4ac is minus 2 squared minus 4 times 1. This gives us 0. So delta is 0, gives a repeated root to the characteristic equation, but we can see this factorizes as a perfect square, so lambda minus 1 all squared equals 0 gives us lambda is equal to 1 repeated twice, right? Because by the fundamental theorem of algebra, the number of roots counting repeats has to be equal to the degree of this polynomial. All right, and so it's there twice. Now, how do we express our homogeneous solution when we have a repeated root? Well, we have y homogeneous is equal to e to the power of that lambda we got times x, and then outside of that we have ax plus b. Let's put a uppercase b there. Okay, so we have it looking like this. So y homogeneous then is e to the power of 1 times x, so e to the x, and then times ax plus b. All right, now let's find our particular solution. So we have a polynomial on the right-hand side, so we're going to guess a polynomial. Now, what's the degree of this? It's 2, so we guess that yp is equal to lowercase a x squared plus lowercase b x plus c. And we want to differentiate this twice. So yp dash is 2ax plus b, yp double dash is 2a. And then we sub these into the differential equation and match coefficients. All right, so substituting this in, we have 2a minus 2 times 2ax plus b, and then plus our yp ax squared plus bx plus c, and so this is equal to x squared minus 1. Okay, now we want to expand the left-hand side and match coefficients, so there are no x squared terms here, so we just have a x squared, and then the coefficient of x is b times x, so we'll write the b and then put the x over here for this bx. And then the product of these is minus 4a and then times x. Okay, so those are the coefficients of the x there. Now the coefficients of x to the power of 0 are, we have now 2a minus 2b for the product of this and this, and then plus c. And so this is x squared minus 1. Okay, so now let's set out matching coefficients. We have a has to be equal to 1, matching this with this, and b minus 4a has to be equal to 0 because there's no single x over here, and then 2a minus 2b plus c is minus 1, matching these coefficients. Okay, well, we already know a is 1, and so b has to be equal to 4 from the second equation, subbing the 1 in there, taking it over to the right-hand side. And so from the third equation, we have c is equal to minus 1 minus 2 times 1 plus 2 times b, which is 8. Okay, so we've just taken the 2a and the minus 2b over to the right-hand side. We still have minus 1. Minus 2 times 1 is minus 2, and then plus 2 times 4 is plus 8. Okay, so we have 8 minus 3 is 5 for C. Okay, so given that, that gives us yp equal to x squared plus 4x plus 5. Okay, which gives us our general solution. Y of x is y homogeneous plus y particular, which is e to the x outside of ax plus b, and then plus x squared plus 4x plus 5. All right, let's move on now to question 7, sorry. Question 7, because we've just done question 6. Okay, question 7 says solve y double dash minus 2y dash plus y is equal to 3e to the 2x. All right, now because the left-hand side is the same as what we had in the last equation, so we already know y homogeneous here is e to the x times ax plus b. And so we guess y particular matching to the same form as what we have here. Now notice the 2x is not the same exponent as the single x. So we're okay here to guess lowercase a e to the 2x. All right, now differentiating, we have yp dash is 2a e to the 2x. Yp double dash is 2 times 2 is 4a e to the 2x. And putting this into the differential equation, we have 4a e to the 2x minus 2 times 2 is 4, a e to the 2x, and then plus a e to the 2x is equal to 3e to the 2x. Okay, now these two vanish, and so we can see matching the two of these that a has to be equal to 3. And so we get our particular solution. Yp is equal to 3 e to the 2x. All right, great. And so now we need to add that to our homogeneous solution. So y as a function of x is y homogeneous plus y particular, which is e to the x ax plus b plus 3e to the 2x. Fantastic. Let's move on to question 8. Okay, now in question 8, we're asked to solve y double dash minus 2y dash plus y is equal to 4 cos of x. All right, we already know that y homogeneous is e to the x times ax plus b. And so we guess a function for y particular that is similar to what we have on the right-hand side. But we need to be general about this, so we'll guess a cos x plus b sine x. Again, lowercase letters because we don't want to get confused with these two. All right, now we need to differentiate this. So yp dash, now the derivative of cos is minus sine, so we have minus a sine of x, and the derivative of sine is cos, so we have plus b cos of x. Okay, differentiating this again, yp double dash is equal to minus a cos of x, and then minus b sine of x. Okay, now we substitute this into the differential equation. So yp double dash minus 2 yp dash plus yp is equal to minus a cos of x minus b sine of x. Okay, then minus 2 times yp dash, which gives us plus, or actually let's put the cos first so we can be tidy about this. So this will be minus 2 b cos of x, and then minus 2 times minus a is plus 2a sine of x, and then we have this to add, plus a cos of x plus b sine of x. Okay, so the sum of all this is supposed to be 4 cos of x. All right, so now we need to collect in terms of cos and sine. Okay, so expanding, collecting in terms of cos and sine. What do we have here? We have minus a for cos of x, then we have minus 2b, and then we have plus a. times cos of x. Now let's look at the sine terms. So we have 2a minus b and then plus b times sine of x, and this is equal to 4 cos of x. Okay, so good. Now let's simplify. So the a's vanish here, and so we get minus 2b has to be equal to 4. And then looking at this, the b's vanish here, and so 2a has to be equal to 0 because there's no sign on the right hand side. So what we get here is, this tells us that a is 0 and b is minus 2. Okay, so now let's have a look at our guess. With a equals 0, we just have minus 2 sine of x. So yp equals minus 2 sine of x. And so now we can write y. Our general solution is y homogeneous plus y particular, which is e to the x ax plus b, and then minus 2 sine of x. Okay, great. Let's move on to question 9. Now, question 9 is a bit of a tricky one. So we're asked to find the general solution of y double dash minus 2y dash plus y equals 3e to the x. Okay, and so I'm going to lead you down an incorrect path first so you can see what's wrong with this. So let's label this, though, a bad guess. Would be yp equals a e to the x. Okay, but first let's remember, since we have the same left-hand side, we do have y homogeneous is equal to e to the x a plus bx. All right, now why is this a bad guess? Well, because the exponents here match in this case, right? So this matches this, and so I don't want to guess something of the same form. All right, but let's see why this is bad. Okay, so if we were to differentiate this, we'd have yp dash is equal to a e to the x. Yp double dash is also equal to a e to the x. And so taking these and subbing this into the differential equation, y double dash minus 2y dash plus y equals a e to the x minus 2a e to the x plus a e to the x. And if we add this together, we get 0. But this is meant to be equal to 3e to the x. This is a contradiction. And so by this I mean a contradiction. It's just shorthand for contradiction. All right, so that's why this is bad. All right, so let's make a good guess now. And so a good guess would be, say, to let yp be equal to ax squared e to the x. And right, remember, I want to get something that's independent to this, right? Because if I find two solutions that are linearly independent, then their sum should give me the general solution to this one. And so I can't pick a e to the x because you see what happens, but I don't want to pick a x e to the x either, because that will not give me something new. That will also give me a bad guess. So this is what I want to pick here. Okay, so differentiating this, we have yp dash is, now we need to use the product rule on this. So differentiating this first one, we have 2ax and then times the other one, and then let's swap those around. So we get ax squared times the derivative of e to the x, which is e to the x. Okay, so here's our first derivative. Now differentiating this again, So we need to use the product rule on this. So we have 2ax times the derivative of e to the x, which is e to the x, and then we swap this around, differentiating 2ax, and so we get 2a, and then times that e to the x. Okay, so we've differentiated this one. Now we have to differentiate this one, but we've already done that to get here, so we'll just copy down what we have above. So plus 2ax e to the x plus a x squared e to the x, and so we can simplify this and call this 2a e to the x plus, we have two of these, so plus 4ax e to the x, and then plus a x squared e to the x. Okay, and so now we want to sub these in, this, and this. So let's put some dot points next to these to identify that these are what we are subbing in. So substituting these into the differential equation, we have 2a e to the x plus 4ax e to the x plus ax squared e to the x, and then minus 2 times this, so which will give us minus 4ax e to the x, and then minus 2a x squared e to the x. Okay, and then plus one of these. All right, all of this together should be equal to 3e to the x. Okay, so let's simplify our left-hand side. Now you can see that a minus 2a plus a gives 0, so none of the x squared e to the x terms. These two vanish, and so we get 2a e to the x is equal to 3e to the x. So 2a is 3, and a is equal to 3 over 2, or 1.5. Okay, so with that then, we have yp is equal to 3 over 2 x squared e to the x is our particular solution. Now the general solution, y of x, is equal to y homogeneous plus y particular, which is e to the x times a plus bx, and then plus 3 over 2 x squared e to the x. All right, so yes, that was a tricky one. Let's move on to question 10, which also looks a little bit tricky. All right. Y double dash minus 2y dash plus y is x e to the x. Okay, so similar story with this one. Now we have our y homogeneous equal to e to the x times a plus bx as before, and we want to guess y particular is ax to the power of 3 times e to the x, because we have an x e to the x here, and the e to the x in here matches an e to the x there, so we want to get an independent solution. So now we differentiate this. Yp dash equals 3ax squared times e to the x plus ax cubed e to the x using the product rule. Now differentiating again, yp double dash, so differentiating this one, we have 6a x e to the x, and then we have plus 3a x squared e to the x, and then differentiating this, well, we already have the derivative of this because we did that here to get this. Okay, and so we just want to write this here to add to that and simplify. And so yp double dash, and I'll put a dot point there, or an asterisk. This is, in the simplified form, we have 6ax e to the x plus 6ax squared e to the x plus ax cubed e to the x. Let's put an asterisk on this and on this as well. Okay, the three of these we want to substitute into our differential equation. And so doing so gives us 6ax e to the x plus 6ax squared e to the x plus ax cubed e to the x. And then so minus 2 times this one gives us minus 2ax cubed e to the x, and then minus 2 times this is minus 6ax squared e to the x, and then plus a single one of these, plus ax cubed e to the x, and so the sum of all this is equal to x e to the x. Okay, so these three vanish, and we're left with 6ax e to the x equal to x e to the x. So clearly we see that 6a is equal to 1, which gives us a is 1/6. And hence yp is 1/6 x cubed e to the x, and so that gives us our general solution to this differential equation, because we add the homogeneous solution to the particular solution, and y of x is equal to e to the x a plus bx, and then plus 1/6 x cubed e to the x. All right, fantastic. Let's move on to question 11, where we have a third order linear differential equation. Okay, this one looks a little bit tricky. So 11 says y triple dash minus 3y double dash plus 3y dash minus y equals e to the x plus 1. All right, so our characteristic equation here is lambda cubed minus 3 lambda squared plus 3 lambda minus 1 is 0. So there's our characteristic equation. But you can see, if you know Pascal's triangle or recognize the expansion here, this factorizes as lambda minus 1 all cubed equals 0. So lambda is equal to 1 repeated 3 times. Okay, and so now our homogeneous solution is e to the power of that lambda, which is 1, times x, and then times a plus bx plus c x squared, all right, because we have a third order differential equation. So here is our homogeneous solution. Now, in the particular solution, we want to guess yp is equal to lowercase a x cubed e to the x and then plus b. All right, now again, we need a cube term times e to the x here because this is an e to the x and we've got an e to the x here. It's not a different number up there in the exponent. Okay, and so differentiating this, yp dash is 3ax squared e to the x plus ax cubed e to the x, and then the derivative of this is 0. Okay, differentiating this again, we have 6ax e to the x plus 3ax squared e to the x, and so that's the derivative of this using the product rule. And then differentiating this, well, we've done that already, it's right here. So let's add to that this. Okay, and so we have our three derivatives. We need to simplify the last one. So 6ax plus 6ax squared plus ax cubed, and this is all times e to the x. Okay, let's put some asterisks here to identify what we are going to sub in. The three of these subbed into, oh no, you know what? We need to differentiate again, don't we? Yeah, we need to differentiate this again. We need a third derivative to sub in. Okay, so let's differentiate this one more time. So yp triple dash is, now let's use the product rule on this one. So differentiating this, we have 6a plus 12ax plus 3ax squared, and then that gets multiplied by e to the x, and then we swap around. And differentiate e to the x this time, but the derivative of e to the x is e to the x, so we just have 6ax plus 6ax squared plus ax cubed, and then times e to the x. Now we need to collect these into a single bracket. Let's change to superscript brackets 3. Okay, and so adding like terms, we have 6a, 12 and 6 is 18, 3 and 6 is 9, and then we have plus a x cubed, and then that's all times e to the x. Okay, good. Now we have enough derivatives to sub in. So substituting in to the ODE, we have this minus 3 of these. Okay, so 6a plus 18 ax plus 9a x squared plus a x cubed. Okay, minus 3 of these. So notice I'm keeping the e to the x out because they all have e to the x in them. Okay, so minus 3 of these will be minus 18 ax. I should look at this one. Okay, minus 18 ax squared, and then minus 3ax cubed for that. Okay, next we're going to sub in plus 3 y dash. So that's plus 3ax cubed for that, and then plus 3 times 3 is 9ax squared for this one. Okay, so we've done the y dash terms. Now we need to subtract y. But here I've got a b on its own, and so what I'm doing is just minus ax cubed, and then I end the bracket times e to the x, and then we have a single lonely minus b. Okay, so the sum of all of this should be equal to e to the x and then plus 1. So clearly b is minus 1 here. All right, now let's simplify what we have in brackets. So these vanish, this and this vanishes, these and these vanish, these two vanish, and so 6a e to the x, then minus b is equal to e to the x minus, or sorry, plus 1, isn't it? Plus 1. Okay, so we have minus b is 1, so b is equal to minus 1, and 6a is 1, so a is equal to 1/6. And so this gives us that yp is equal to 1/6 x cubed e to the x minus 1. So the general solution here, y of x, is equal to the homogeneous solution plus the particular solution. So we have, let's see, can I factorize this in my head? I'll try. E to the x outside of a plus bx plus cx squared, and then plus 1/6 x cubed, and this is all times e to the x, okay, and then we have this lonely minus 1. And here's our general solution. Okay, so we have now solved question 11. Great, let's move on to question 12, where we have an initial value problem. Grab a little bit more paper. So here we've got to solve the initial value problem. X double dash plus 3x dash plus 2x is equal to 1 minus 2t squared, where we have x of 0 is 0 and x dash of 0 is minus 4. Okay, so here we first need to find a homogeneous solution. So this is x and t's. So x homogeneous comes from solving the characteristic equation lambda squared plus 3 lambda plus 2 equals 0. Okay, this one looks easy to factorize. So we have lambda plus 1 lambda plus 2 equals 0, because the sum of 1 and 2 gives us 3, and the product of 1 and 2 is 2. Okay, and so lambda 1 is minus 1, and lambda 2 is minus 2. So given this, we can write our homogeneous solution. X homogeneous is equal to a e to the lambda 1, so minus x, and then plus b e to the minus 2x. Oh no, it's not an x, isn't it? It's a t. So change those x's into t's. All right? Because t is our independent variable here. All right, so great. We have the homogeneous solution. Now we need to make a guess based on what the right-hand side looks like. So we'll guess x particular equals lowercase a t squared plus lowercase b times t plus lowercase c. And we need to differentiate this 2 times. So xp dash is 2at plus b. xp double dash is 2a. And then we sub these into our differential equation and compare to get the lowercase a, b, and c. Okay, so subbing in 2a plus 3 times this is 3b plus 6 a t, and then 2 times this is 2c plus 2bt plus 2at squared, and all of this is meant to be 1 minus 2t squared. Okay, now let's collect in terms of coefficients of the t. So we have 2a plus 3b and then plus 2c. This has to match with 1. Okay, the coefficients of t, 6a plus 2b, and that's it. There are none of the single t's on the right hand side, so that's 0. And then the coefficients of t squared, so 2a has to be equal to minus 2. All right, so we have a system of 3 linear equations in 3 unknowns, lowercase a, b, and c. So solving this is easy, right? So from the third equation we get a has to be equal to minus 1. Okay, and so if lowercase a is minus 1, we put it in here, we get minus 6. So 2b is plus 6. Dividing that by 2, we get b is 3. Okay, and so lowercase b is 3. Sub that into our first equation, and we have minus 2 plus 3 times 3 is 9, plus 2c is 1. So this is 7 here. 1 minus 7 is minus 6, so 2c is minus 6, and so c is minus 3. Okay, let's just double check. Minus 2 plus 9. 9 minus 2 is 7. 7 minus 6. Yes, that's 1. Okay, so that works out just fine. So that gives us our particular solution. xp is equal to minus t squared plus 3t minus 3. Okay, super. Now let's add together the homogeneous solution that we got earlier. So our general solution is x of t is equal to a e to the minus t plus b e to the minus 2t minus t squared plus 3t minus 3. Okay, so here's our general solution, but remember, we have two initial values which allow us to find our uppercase A and uppercase B, these two. So we'll say since x of 0 is 0, we have 0 is equal to A e to the 0 is 1 plus B e to the 0 is 1, and then minus 0 squared plus 3 times 0 minus 3, and this is meant to be equal to 0, right? Right hand side is 0. Okay, so let's simplify this. So that says A plus B is equal to 3. All right, and so with this, we want to now differentiate and use our second condition to get another equation in uppercase A and B. All right, so we need to set this page aside, or at least write down what we got from it. Okay, so far we have x homogeneous is A e to the minus t plus b e to the minus 2t. We know our particular solution is minus t squared plus 3t minus 3. And so we also have a plus b is equal to 3. Okay, next we have to use x dash of 0 is minus 4. So we need to differentiate our general solution, which remember was the sum of these two. All right, so x dash of t equals, so differentiating the first part of this, we have minus a e to the minus t, and we have minus 2b e to the minus 2t, and then for the derivative of this part, we have minus 2t and then plus 3. So here's our derivative. So using x dash of 0 is minus 4, subbing 0 in for the t, we have minus a e to the 0 is 1, minus 2b, again e to the 0 is 1, and then minus 2 times 0, and then plus 3, this is equal to minus 4. Okay, putting this all together, we now have the system a plus b is 3, and then this, we can write this as a, let's keep it, minus a minus 2b equals minus 7. Okay, taking the 3 over, we have minus 7. So now it's clear that we can add the two equations and the a's will vanish. So adding equations, we have b minus 2b is minus b is equal to 3 minus 7 is minus 4. And so b is equal to 4. Okay, so if b is 4, then we get a is 3 minus 4 is minus 1. And so this gives us our solution to the initial value problem. So x of t is equal to minus e to the minus t plus 4 e to the minus 2t minus t squared plus 3t minus 3. Okay, so let's move on to the next question since we have now finished question 12. So question 13 says solve the initial value problem x double dash plus 4x dash plus 4x is 2 e to the minus 2t with x of 0 is 1 and x dash of 0 is also 1. Okay, so we need to begin by writing down our characteristic equation, which is this. Now this has discriminant 0, so we have a repeated root here and it's a perfect square. So lambda is minus 2 repeated. And remember what our solution looks like here. X homogeneous is equal to e to the power of minus 2 times t. And then we have a plus bt. Okay, now for the particular solution, notice on the right-hand side we have the same exponent as we have here, which makes this harder. So what we want to guess is that x particular is equal to a t squared e to the minus 2t. Okay, so differentiating this, xp dash is, we need to use the product rule here. So we have the derivative of e to the minus 2t is minus 2 e to the minus 2t. So minus 2 at squared e to the minus 2t. And then swapping around, we have e to the minus 2t times the derivative of at squared, which is plus 2 at e to the minus 2t. Okay, and so let's factorize the e to the minus 2t out. So we have xp dash is minus 2at squared plus 2at times e to the minus 2t, in case we need that. All right. That looks fine to me. All right, let's differentiate again because we need a second derivative to sub in here. So xp double dash is now just differentiating this. Actually, you know what? Let's use the product rule on this one. So minus 2 2a squared plus 2at e to the minus 2t. So what I've done is differentiated this and multiplied the result by this. And then I want to reverse the order of that. And so now we will differentiate this one and multiply it by this. So the derivative of minus 2at squared is minus 4at. The derivative of 2at is plus 2a. And then we still have our e to the minus 2t. Okay, we want to factorize out the e to the minus 2t because it'll make this convenient for us. So xp double dash is, let's put that minus 2 back in. So here we have 4a t squared. Then we have minus 4at. But we also have a minus 4at here, so that gives us minus 8at. And then we have a plus 2a, and that's all times e to the minus 2t. All right, put an asterisk here. Let's put an asterisk here. and an asterisk here. Okay, so these three we sub into the left-hand side. So then we have 4at squared minus 8at plus 2a times e to the minus 2t, but I'll leave that for last. Okay, and then 4 of these, which gives us minus 8at squared plus 8at, and then we have a plus another 4 of these. So plus 4at squared, and all of this is times e to the minus 2t. And then this is equal to a right-hand side 2e to the minus 2t. All right, so now let's simplify what is inside the bracket. So our t squared terms, they will vanish. 8at minus 8at gives 0, so we just have a single 2a there. So 2a e to the minus 2t is 2e to the minus 2t. So clearly we have a equal to 1. Okay, and so let's use that and say xp is equal to t squared e to the minus 2t, and now let's add that to our homogeneous solution. So x as a function of t is equal to e to the minus 2t outside of a plus bt, and then we also had, in our particular solution, we had a t squared. So t squared e to the minus 2t. So here's our general solution. All right, and now it's time to use x of 0 as 1. So using x of 0 equals 1, now if we sub in 0 for t, we've got a, and then we have plus 0, so a times e to the 0 is equal to 1. So we've just subbed in t is 0 here, here, and here. What we're left with is a single a e to the 0, so a equals 1. Okay, now let's collect what we've learned. So we have x of t is equal to e to the minus 2t times a is 1, so 1 plus bt plus t squared. Okay, we also have x dash of 0 is 1. So we need to differentiate this in order to use our initial value, x dash of 0 is 1, in order to get uppercase B. All right? So let's differentiate this now. X dash of t. So let's use the product rule on this. So we have minus 2 e to the minus 2t for the derivative of e to the minus 2t, and then times 1 plus b t plus t squared. And then we swap the order of this using the product rule. So e to the minus 2t times the derivative of 1 plus bt plus t squared, which is b plus 2t. Okay, so here is our derivative, but let's collect in terms of e to the minus 2t. So we have then e to the minus 2t outside of b, now putting the minus 2 back in, so b minus 2, and then we have plus 2t, that's the 2t I'm talking about, and then over here we have minus 2 times b, okay, and then we have minus 2t squared. All right, so here is x dash. So using x dash of 0 equals 1, replacing the t's with zeros here, we have then b minus 2 e to the power of 0. So this is equal to 1, and so we get b equal to 2 plus 1 is 3. All right, and so this gives us our solution to the differential equation. X dash of t is equal to e to the minus 2t 1 plus 3t plus t squared. Okay, and I think I will stop there. Thanks.